Witten from Princeton. This morning's lecture is entitled Islands and Entropy, and we are really honored to have Professor Witten to share it with us. Thank you.
Thank you. So yesterday we discussed the basic idea of the Bekenstein-Hawking entropy of a black hole, and we remember that the black or observes the quantum fields only outside the horizon. So there was a horizon in space-time, and you see only the outside. And somehow, observing the quantum fields only outside the horizon causes what you observe to have a thermal nature. So now we're going to begin today by exploring this in a more basic, or more, if you like, more elementary setup. We'll just be in Minkowski space. With coordinates time and also space. And we're going to suppose that you measure only, well, let me describe it in a Lorentz invariant way. In a Lorentz invariant way, I'm going to only draw two coordinates, t and x. I'll suppress y and z in the pictures. And then I'm going to suppose, so here's the origin. And then I've drawn the two light rays through the origin. But you should imagine continuing the picture into the blackboard. So those light rays are really null planes that are independent of translations in the y and z directions. And I'm going to suppose that the observer is located in what's called the right rindler wedge. The rindler wedge is this region here, to the right of the light cone, to the right, to the future of the past horizon and to the past of the future horizon. That wedge on the right. So if I use light cone coordinates u and v, it would be the region where u is positive and v is negative. A way to describe why we're making observations in the rindler wedge following Unruh is to imagine an observer who's accelerating in such a way that what you can see is bounded by the rindler wedge. So the observer is on a hyperbolic orbit, constant acceleration. I haven't drawn it very well. It'll be asymptotic to these null planes. And relativistic causality will only let such an observer see what's in the rindler wedge. However, for what I'll say, we don't have to commit ourselves to the vantage point of such an observer. We just assume, for whatever reasons, we imagine observations made in the rindler wedge only. And we want to see what would be the right mathematical framework to describe such observations. And we're going to look at the vacuum as seen in the rindler wedge. So first we should describe the vacuum if you can see all of space. We can regard a quantum state for a quantum field as a function of the field values on a Cauchy hypersurface, an initial value surface. And in Minkowski space, an obvious initial value surface would be in some Lorentz frame to take the surface times 0. Actually, let me even, for the moment, erase the light rays. First step is just to describe the vacuum state Well, up to a normalization factor, the vacuum state is prepared by a path integral in Euclidean signature on a half plane. So we go to Euclidean signature. And we do a path integral. So now the surface t equals 0 is also tau equals 0. But we now do a path integral over the half plane in Euclidean signature. Not half plane, half space in Euclidean signature from tau equals minus infinity to 0. And the vacuum wave function of a quantum field phi up to a constant normalization factor is simply the path integral. You do a path integral with the boundary conditions that phi restricted to tau equals 0 is some given function phi of x. And you integrate over all fields in the bottom half space with that boundary condition. That will give, up to a normalization factor, that will give the vacuum wave function. It's the integral over all the quantum fields with this boundary condition that phi on the boundary is the given function phi of x. Now I want to distinguish bras and kets. So I'll think of this as a preparation, actually, of the ground state wave function regarded as a ket. If we want to prepare the corresponding bra, we do the same thing, but we prepare it by path integral in the upper half space. We do a path integral over the region from tau equals infinity to tau equals 0 with the same boundary condition. And again, up to a normalization factor, the path integral with the boundary condition prepares the vacuum wave function regarded now as a bra. Well, what would be the projection operator onto the vacuum? The projection operator into the vacuum, the pure state density matrix of the vacuum is just the bra times the ket. So here we rather stupidly have an integral over two half spaces in each case with the boundary condition that the boundary values of the field is some function phi of x or phi tilde of x. The only subtlety is that the two functions are different in general. So the ket is a functional of one function phi. The bra is a functional of another function phi tilde. After all, the density matrix is supposed to be a matrix or an operator. A matrix or an operator has an initial, it maps an initial state to a final state. If you visualize it as a matrix, a density matrix would be literally a matrix with an initial and final index I and j. But here, since we're doing quantum field theory, the initial and final index is replaced by state of the quantum field. So the density matrix takes as input one specified field phi tilde, and as output an entirely different specified field phi, with no relationship between them. Now, of course, we haven't learned very much by just stupidly multiplying the bra times the ket and not doing anything in particular. But suppose we're planning to make only observations in the right rindler wedge. So if I draw that picture again, well, the right rindler wedge is the region that's causally determined by what happens for x positive. Is there a problem with seeing the blackboard or anything? Well, first of all, can you in the middle see the blackboard? And how about people in the back? We're supposed to use the screen. Okay. I'm going to assume, unless somebody complains, I'm going to assume you can see the blackboard. So you're not allowed to complain after the lecture. Okay. So, you see, relativistic causality says that everything that happens in the right rindler wedge is determined by the state of the quantum fields at positive x. So, to get a density matrix that will describe the right rindler wedge, we want a density matrix for the fields at positive x, but we're not planning to observe the fields at negative x. Relativistic causality also says we should forget about the fields at negative x, because whatever happens at negative x can't influence the right rindler wedge by signals traveling slower than light. So we want to integrate out or trace over the fields in the left half space x negative. What that means is that we want to take a partial trace over the fields in the left half. What that means is that we take the initial and final states to be equal and sum over them. Well, in quantum field theory, what would it mean to set the initial and final fields in negative x equal and sum over them? What it means is that we glue together the top and bottom of the picture and integrate over those fields. So instead of trying to edit that drawing, I'll draw this one for a simple contrast. The picture is now going to look like this. The dotted line is where the gluing has occurred. Here is positive tau, and here is negative tau. So you see, now we're doing an integral over the whole space, except there's a cut on the positive x-axis. And the fields are allowed to be discontinuous across the cut. Since we glued on the left, and then we integrate over we glued together the top and bottom, but we also integrate over the value of the field on this part of the axis. And since we're integrating above, integrating below, and also integrating on the axis, I just erase it over here. We integrate freely over the fields in all the space except for a cut on the positive x-axis. And on the positive x-axis, we allow discontinuity. So the fields above are in general different from the fields below. So this picture, the path integral in this picture, represents the Rindler density matrix. It represents the density matrix for an observer who's making observations only in the Rindler wedge. Now, we can describe it in a slightly different way, though. Well, okay. First of all, I should acknowledge that this picture is a little bit vague near the point x, near the surface x equals 0, because at positive x, we allow a discontinuity between above and below, but continuity seems to say it should be continuous at the end. And this is a little bit singular near the endpoint at x equals 0, and that's true. And I think it's true that fair to say that the reasoning I'm giving is not truly mathematically rigorous, and that fact actually leads to ultraviolet subtleties. But although it's difficult to completely justify it mathematically, it's also true that this kind of reasoning gives very useful and important results. Thank you. Good thinking. Now we're going to look at the picture in a different way. We imagine we have a state that's defined only for positive x or non-negative x. And then we define the operator, which I think I'll call k. In Lorentz signature, it would be a Lorentz boost generator. Except that, well, with the Lorentz boost generator, if I take the integral from minus infinity to infinity. Instead, though, I'm going to take the integral only from 0 to infinity. I'll call it k sub r, where r is for right. This is the Lorentz boost generator for fields on the right half space. But in Euclidean signature, kr generates a rotation. Not a boost. Because if you take the formulas for a Lorentz boost in Minkowski space and replace t by it, a Lorentz boost turns into a rotation. The coshers and sin's turn into cosines and sines, and you get a rotation. So if you take the operator e to the minus theta kr, the operator e to the minus theta kr applied to an initial state psi will produce a final state that you could get by a path integral on a wedge of angle theta. So you see, I'm taking not e to the, in Minkowski space, we would take the boost generator, and then we would do e to the minus I theta kr with the Lorentz boost with a rapidity theta. I've replaced theta by I theta, and a Lorentz boost with an imaginary rapidity is a rotation of Euclidean space. So e to the minus theta kr as an operator means that you take the wedge, you have an initial state, you do a path integral on the wedge with boundary conditions, let's say I'll call them in and out. The in boundary condition is given by some given phi, and the out boundary condition is phi tilde. If you want to represent it as an operator, the operator e to the minus theta kr, if you want to calculate its matrix element between an initial and final state, phi and phi tilde, you would do a path integral on the wedge with initial and final boundary conditions given by phi and phi tilde. Oh, okay, sorry. Now we have the rindler density matrix was an integral over the whole plane with a cut on the positive axis. But you see, the cut plane is equal to a wedge with theta equals 2 pi. If we take this wedge with the general angle theta, what I said theta equals 2 pi will go all the way around. But unless we take a trace, we get an operator with separate initial and final states, phi and phi tilde. So without taking a trace, we'll get an operator, a matrix, a density matrix. So we conclude that the density matrix of Rindler space apart from a normalization constant that I'll call C, is e to the minus 2 pi kr. The reason the normalization factor is there is that it was here in the beginning. When we constructed the vacuum, we needed a normalization constant to get the normalized vacuum state. Then when we had the pure state density matrix for the vacuum, it had a normalization factor. And when we get over here, we still have a normalization factor, which is supposed to ensure the fact that rho rindler is a density matrix. The trace of rho rindler is 1. You would take the trace by gluing together the top and the bottom and integrating over everything. And so the trace would just be a path integral in the whole plane. So the normalization factor is also the path integral in the whole plane. Now let's look at the result we've learned. We have kr equals integral from 0 to infinity dx x times t0, 0. And suppose you make local measurements at some value of x. For example, x is approximately rho. Oh, sorry, rho is density matrix. X is approximately capital R. Well, unfortunately, capital R was for the right rindler wedge. Okay, we'll go with L. Then, near x equals L, well, in excitations that are localized near x equals L, kr is approximately L times the Hamiltonian. And so the density matrix is approximately e to the minus 2 pi L times the Hamiltonian. This is just the Hamiltonian. And therefore, we see that the Rindler observer at distance L from the Rindler wedge sees approximately a thermal ensemble with beta equals 2 pi L, or a temperature, which is 1 over 2 pi L. Now, it's important to not exaggerate how much this is true. So you see, in thermal equilibrium, the temperature is constant throughout space. And then the meaning of temperature is completely well-defined. The notion of temperature is approximately well-defined to the extent that temperature is nearly constant. In this problem, the temperature is not sufficiently constant to make that true, because nearly constant would mean that over a length scale of order 1 over the temperature doesn't change significantly. But that's not true here, because if we're making observations at a length L, and the temperature is 1 over L, within a distance L, which is 1 over the temperature goes from infinity to half of this value. So we're not really close to thermal equilibrium, and therefore it's only a very rough description to say that this is like a thermal ensemble. Okay, You can't think of this as like a thermal ensemble in Minkowski space. We can see in another way what the limitation is. Let's draw the Rindler state picture again, and we're trying to make observations in the right Rindler wedge. If you're going to distinguish a temperature of 1 over 2 pi L from 0, your observation will take a time longer than L. So you can't be at rest. If you're at rest, you'll leave the Rindler wedge in a time L. This was L, so you'll leave the Rindler wedge in a time L. So you can't detect this temperature if you're at rest. To detect it, you have to remain in the Rindler wedge for a time long compared to L. And the way to remain in the Rindler wedge for a time long compared to L is to accelerate. And a mathematically precise version of the statements, which is due originally to Unruh in about 1976, or 5 maybe, a little bit after Hawking, is that a uniformly accelerated observer makes observations that are thermal in the sense that they obey the general axioms for equilibrium observations at temperature T. They have the right analytic properties. I won't go into that degree of detail about it. We're going to just think of this as an informal statement that at a distance L, the temperature is 1 over 2 pi L. Meaning, therefore, that the temperature is very close, very large, near the bifurcation surface. So the bifurcation surface where the future and past light cones meet is the analog of what I called the bifurcation surface when we were discussing the black hole yesterday. The intersection of the past and future horizons, I called it the bifurcation surface yesterday. And that's the analog of this surface at L equals 0, where the temperature defined this way would diverge. Now, Rindler space is actually very similar to the black hole near the horizon, although it's not similar to the black hole far away. In other words, the Kruskal-Sakara's analytic continuation of the Schwarzschild solution past the horizon shows that the near horizon geometry is completely smooth, just like this geometry near the Rindler horizon is smooth. So the calculation we've done is actually very similar to what was going. See, in this calculation, all we did was to put in the fact that we're making observations only in part of space-time. And we deduced from that, in a certain sense, thermal behavior. Now, here it was an arbitrary assumption, although you could justify it, well, as a mathematical exercise, you can justify it by imagining a uniformly accelerated observer, although good luck in creating such a creature and equipping that person with the rocket ship that will power the uniform acceleration. But in the case of a black hole, just an innocent observer who tries to remain safely outside the black hole horizon has this property of making observations only in part of the space-time. So in the black hole case, the important part of this calculation is making observations only in part of the space-time, which is also the important part of the black hole calculation. So the point of what we've done today is to try to explain in isolation what was really leading to yesterday's answer. So I'm going to go back to the black hole in a second, but maybe I'll stop here for questions on Rindler space. No luck?
Is this temperature, the Uru temperature, related to the acceleration of the Rindler observer?
Yes, because if the Rindler, how fast you have to accelerate to remain at a proper distance L from the horizon, which here means this point, is inversely proportional to L. So the temperature you observe is directly proportional to how fast you're accelerating. Well, all we did was to reinterpret the vacuum state in Minkowski space for an observer who only makes observations in the right Rindler wedge. So we're simply discussing the vacuum. If you and I are at rest, we see the vacuum. the accelerated observer, we can see all of space in principle, and we see nothing. We see empty space.
So this is the same that we have seen yesterday with the Hawking temperature. It's the same thing, but with another metric. Yesterday we used the sparse metric, and now...
Well, in each case, we studied an observer who only measures the fields in part of the space-time. And we discovered that that results in seeing approximately thermal behavior. In rindler space, the thermality, well, there's a rigorous version where you actually consider the accelerated observer, but you never are thermal with Minkowski space thermal correlators because X isn't sufficiently constant. It varies too rapidly. It always varies on a scale proportional to the inverse temperature. Whereas in the black hole case, the temperature approaches a constant as you're infinitely far away. In fact, we did the calculation yesterday from the vantage point of an observer at infinity. So there it's completely unambiguous that an observer at infinity does not see vacuum correlation functions, but sees thermal correlation functions at the Hawking temperature. Yesterday, we were discussing what would be observed by an observer at rest near infinity. Infinity just means sufficiently far away. So if it's a solar mass black hole, radius of a few kilometers, if you're 1 million kilometers away, that's infinity from yesterday's point of view. But today, to observe this effect, you have to accelerate sufficiently that you never fall behind the Rindler horizon. Because if you do fall behind the Rindler horizon, you'll see beyond the Rindler horizon. This is an effect for people who are limited to stay inside Rindler space. This, which means that asymptotically you have to start accelerating. Any other questions?
So suppose that I am the accelerator observer and I have a detector, and the detector clicks. So that's an invariant statement. So suppose now I am the inertial observer and I see the detector clicking. How do I explain it?
Well, the detector can emit as well as absorbing radiation. If you're an accelerated observer, if you have a detector, your detector is some quantum device that interacts with the quantum fields. So the quantum fields aren't free. They couple to your detector. The observer at rest will say that the accelerated observer emitted what that person later detected. But the accelerated observer is simply trying to measure whatever is there, and we'll see thermal correlators.
I see.
Other questions?
If you can just clarify how you got the numerical result there. So you are evaluating the operator Kr on a particular state of the trajectory which you depicted there, which has a minimum distance from x equals 0 equal 12, or how did you...
You're asking to model in more detail what the Rindler observer sees? Is that the question?
How, from the general formula for the
yes.
raw Rindler, how did you get that?
Well, I only gave an informal explanation of why Rindler space is thermal. I said that if we can treat x as constant, which for an observer, so if you're an accelerated observer and you're only making measurements along the trajectories, then x is very nearly constant. That's why you can make a mathematical precise statement in Unruh's context. A more informal statement, though, is that if for any reason x can be treated approximately as constant, then e to the minus 2 pi k is a thermal density matrix with the inverse temperature being 2 pi times the effective value of x. I wasn't intending to try to go into more detail than that about the Rindler observer. The Rindler observer is just a person for whom x is effectively constant because observations are only made at a given x. And the precise statement of thermality is that correlators you'll measure satisfy what's called the KMS condition, which is a criterion for thermality. It's not true that you have thermality with the Minkowski space Hamiltonian. I see another question back there.
Only for the sake of clarity and just for the future, I just want to know which choice of observer, or better to say, detector, which choice of...
It doesn't matter, just as it didn't matter yesterday. All that mattered yesterday was that we were making measurements in the asymptotic future far from the black hole. All that really matters today is that we're making measurements only in the rindler region for whatever reason. A physical model of that why that might be true is that the observations perhaps are made by an accelerated observer. And then the density matrix for such an observation is this e to the minus 2 pi kr. But what you'll observe with that density matrix, of course, depends on exactly what you measure. I think maybe I'll go on now, and we'll discuss the Euclidean. So now we're going to discuss the Euclidean picture of black hole thermodynamics. And that will have some synergy with what I've just explained for rindler space. So we start with the Schwarzschild. Here I'm going to follow Gibbons and Hawking. Not too long after Hawking's discovery of black hole evaporation. So we start with the Minkowski space metric. And we're going to go to Euclidean signature. Okay, of course, this metric has a well-known singularity at r equals 2 gm, which confused people for a long time. Now, Gibbons and Hawking said to go to Euclidean space by t equals minus I tau. So to the metric, all that happens is we replace minus dt squared with plus d tau squared. Gibbons and Hawking discovered this is actually a smooth metric if we interpret it properly. To see that, we're going to expand near r equals 2 gm. We let r equals 2 gm plus rho squared. So 1 minus 2 gm over r is approximately rho squared over 2 gm plus order rho to the fourth. So I can rewrite the metric. Sorry, I also should worry about the r squared. So dr is 2 rho d rho. So dr squared is 4 rho squared d rho squared. And you see, the point of this is that the rho squareds cancel out in this term. So this term becomes, well, this term, first of all, 1 minus 2 gm over r is rho squared over 2 gm. Here we get 4 d rho squared times 2 gm, well, 1 over 2 gm. then r squared d omega squared becomes harmless. We can just replace r by 2gm squared. And here we've expanded near the horizon, so there are corrections of order rho squared to everything. We're not going to care about those corrections. All we care about is that they're smooth. We're going to investigate the behavior near the horizon, and we'll see that this metric is also smooth. So for example, this term is obviously harmless just because r is not going to 0 at the horizon. That's just a smooth metric. This is the metric of a sphere of radius 2gm. And these two terms we can write as 8gm times d rho squared plus rho squared d tau squared times something according to my notes, that's rho squared over 16g squared m squared. So the metric is this, and then there's the 2gm squared d omega squared. And then there are higher order terms that we're ignoring. Now the insight of Gibbons and Hawking is that this is essentially a smooth metric. Something that you all know is that d rho squared plus rho squared d theta squared is the metric of the plane in polar coordinates. And that's completely smooth if and only if theta is equivalent to theta plus 2 pi. So it's the same here, except that we have this extra factor of 16g squared m squared in the denominator. So it's tau over 4gm should be equivalent to tau over 4gm plus 2 pi. In other words, tau is equivalent to tau plus 8gm times pi. So we've discovered that in Euclidean space, we have a completely smooth metric provided we consider tau to be a periodic variable with period 8 pi gm. While periodicity in imaginary time corresponds to thermal correlators, corresponds to thermal behavior in quantum field theory. So we found a sign of thermal behavior at a temperature which is the inverse of the period, the Hawking temperature, 1 over 8 pi gm, which is the same answer we got yesterday. Now, to a lot of people, this derivation seems much quicker and simpler than the Lorentz signature derivation as usually presented. I tried to present the Lorentz signature derivation yesterday in such a way that was almost as simple as this, or maybe did seem as simple as this. The reason I wanted to start in Lorentz signature is that physics is really in Lorentz signature. And I think you miss a lot if you only have the Euclidean derivation of the Hawking effect. Because that would leave me at least not feeling I don't really understand what it means. But once one understands what it means, because one has the Lorentz signature derivation in one's toolkit, which was the main purpose of yesterday's lecture, then one finds that the Euclidean approach is actually very powerful, as is illustrated by the fact that it took about 10 minutes to explain it just now. Now, we're going to now imitate what we did before in rindler space. Remember, to prepare the vacuum, we did a path integral on a half space. What did that mean from an abstract point of view? It means that we selected an initial value surface, which was time 0. And then we did a Euclidean path integral to the past of that hypersurface. And here we were discussing a quantum field theory in Minkowski space. So the past meant the past half-plane in Euclidean signature. In gravity, though, the theory defines what its own past is. So, well, okay. We're going to take this space-time. Okay. First of all, it's manifest that it is true that near the horizon, this was like rindler space, right? We got a flat space metric near the horizon in the Euclidean version. And in the rindler discussion, it was flat everywhere, and in particular, it was flat near the horizon. But in this derivation, the Hawking temperature came entirely from making the geometry smooth near the horizon. So that shows that the Hawking effect was equivalent to making observations. Well, it was completely equivalent. It was all, in this derivation, all we did was to make the geometry in Euclidean signature smooth near the horizon. So we were just studying the vicinity of the bifurcation points in rindler spacetime. And that local behavior led to the Hawking temperature. In the global rindler space, the temperature falls off as, I think it was 1/2 pi times the distance. In the Hawking case, the geometry is different. So, remember, the geometry was this d tau squared times 1 minus 2gm over r. Now, for what I'm going to explain, we're not very interested in these angles. We're just interested in this two-dimensional geometry. And tau, we learned we should interpret it as being equivalent to itself plus 1/8 pi gm. Oh, sorry, not 1/8 pi gm. And as r goes to infinity, the coefficient of d tau squared is 1. So at large r, the geometry is a cylinder. But then you go into smaller r, and this coefficient becomes smaller. And eventually, at what used to be the horizon, it goes to 0. So you could describe, well, I'm suppressing the polar angles, just as we did yesterday in drawing Penrose's diagrams. Penrose diagrams. With the polar angles suppressed, you could describe the Euclidean geometry as what you could call a semi-infinite cigar. It goes off to infinity. I've drawn it a little bit irregularly, but it's, of course, rotation invariant. And it's asymptotic just to r times a circle at infinity, where the circle has radius 8 pi gm. So a Euclidean path integral would be a path integral in this space. But now I want to describe to you the Hartle-Hawking Israel state, which is the state of a black hole in thermal equilibrium. To get that, we simply are going to take an initial value surface that we can use on which to define a state of the quantum field. The initial value surface will take the reflection tau goes to minus tau. We'll take its fixed point set. Well, what's the fixed point set of tau going to minus tau? Of course, tau equals 0 is a fixed point. but also tau equals 4 pi gm. Because tau is only well-defined modulo tau going to tau plus 8 pi gm. So 0 and 4 pi gm are both. We make a reflection of the cigar that exchanges the top and bottom. It leaves fixed this line on the front, but it also leaves fixed a line on the back. And it curls around in here. Okay? And we regard this as an initial value surface. So this surface S is our initial value surface. And now we're going to make a quantum state psi S. What do I call it? Well, maybe I'll call it psi HHI. HHI is for Hartle-Hawking Israel, the people who introduced this state. So psi HHI of phi. It's a function of phi on the initial value surface S. So phi S of x is just phi on S. We do a path integral over the past. So S divides this Euclidean black hole geometry into two pieces, the upper part and the lower part. We do a path integral in the lower part with boundary values given by phi on the region S. I'll call it BH minus, black hole minus. So the bottom part is BH minus, the top part is BH plus. A path integral in BH minus with boundary condition that phi restricted to S equals phi S of x. So in formulas, you have to divide by a normalizing constant. A path integral in the bottom half of the Euclidean black hole with given boundary values gives a quantum state of the quantum fields on the hypersurface S. Well, what is the hypersurface S? In Lorentz signature, well, first of all, at large R, the geometry is flat. And that remains true when you continue to Lorentz signature. But you have the front and back of the picture. And both the front and the back are two asymptotically flat regions in Euclidean signature. And they will each continue to an asymptotically flat region in Lorentz signature. So if Kruskal and Sakaras and other people who discovered the maximal extension of the Schwarzschild solution had known this Euclidean picture, their job would have been much easier to discover the two-sided geometry. The two-sided extension, so the Penrose diagram for maximal Schwarzschild, I'm going to draw it in asymptotically Minkowski space. Yesterday on one of the transparencies, I had a de Sitter version. But this is the right asymptotically flat region. And here's the left asymptotically flat region. So in Euclidean signature, we have S plus, let's say, or S right, I'll call it, and S left. S right is the asymptotic region where tau is 0. S left is the asymptotic region where tau is 4 pi. But they're equivalent to each other by a rotation of the picture. They remain equivalent in Lorentz signature. So S right is over here, and S left is over here. So the Hartle-Hawking Israel state, which is a state of the quantum fields on the hypersurface S, its Lorentz signature interpretation is that it's a state of the quantum fields in the maximally extended Schwarzschild spacetime with two asymptotically flat regions. So it's one, there are two asymptotically flat regions, and in the interior there's a wormhole between them, but it's a wormhole with this funny property that you can't travel from one side to the other. If you try, you end up at the singularity. Traveling no faster than light, you can't get from one side to the other. So the two are connected, but not in a way that lets you communicate. And the Hartle-Hawking Israel state is a natural state in this two-sided universe. And we'll discuss its physical interpretation next, but maybe we should take the break here.
So we are going now to have a 30 minutes coffee break, but before that, we are going to take a picture here on the outside, on the staircases. Okay. So please, first the picture, and then we go to take a coffee.
We'll start with questions on this derivation. So if you had any questions and you don't get to ask me during the break, you can ask just when we start.
Okay. Okay, but then we have a session on questions. That's at the end of it.
Okay, but some questions.
I know.
Se no ne facciamo alla ripresa. Va bene? Torniamo a parte, dai.
Possiamo cominciare? Okay, so before starting, we can take one more picture. And yeah, if there are questions about the previous part, they are welcome now.
Okay, some questions were asked during the break, so maybe
Yeah,
we heard all the questions.
Yeah, indeed. So we can start the second part of the lecture.
So the last thing I explained was the definition of the Hartle-Hawking Israel state. I'll just draw it bigger. Sorry. Here's the Euclidean black hole with 2 extra dimensions suppressed. It's a kind of semi-infinite cigar. And here is the initial value surface, which I called S. It was tau equals 0 and 4 pi gm. And the two meet at the point r equals 2 gm and tau equals 0, that the bifurcation point of the two horizons in the Lorentz signature point of view. And this is a state in the Hilbert space of 2 asymptotically flat worlds. There is an asymptotically flat world on the right that corresponds to this region, tau equals 0, corresponds to the right in the Lorentz picture. And then there's a region on the left that corresponds to tau equals 4 pi gm. So there are 2 perfectly good asymptotically flat worlds. And we constructed a single Hilbert space in the product of the 2. So if H left, H right are the Hilbert spaces of a left or right observer, then the state we constructed is in the tensor product H left tensor H right. Now, we could ask what would be the physics seen by one observer. After all, these left and right observers can't communicate with each other. So any observer is only experiencing one side or the other. Well, if you want to see both, you can, at least according to classical general relativity. All you have to do is to fall behind the horizon. Then you can see both worlds for a short time before your life ends at the singularity. But for those who want to on one side or the other, and then they can see only one of these two worlds. So we want to discuss what the world looks like to an observer who just sees one of the two worlds. So if you understood the first part of the lecture, you perhaps know what to do. You take the pure state density matrix of the Hartle-Hawking Israel state. Now the ket was obtained by the integral on the bottom half of the black hole spacetime. And the bra would similarly be obtained by path integral on the top half. So the stupid product of the two path integrals with no connection between them would give the pure state density matrix of the Hartle-Hawking Israel state. But suppose we want the density matrix for the right observer only. To get the density matrix for the right observer, we take the trace over the Hilbert space of the left observer of the Hartle-Hawking Israel state times the corresponding bra. We take the trace of the observations of one observer of the pure state density matrix. Now, we already did that once in the case of Minkowski space, so we do the same thing again. If we want to sum over all the observations made on the left side is where I've drawn the dotted line. And in the pure state density matrix, the fields are discontinuous across the surface S. There's one field on the bottom with S regarded as the boundary of the bottom. There's one field with S regarded as the boundary of the top. There's another field. They're the two fields that enter in the bra and the ket. Two fields phi and phi tilde on the top or bottom of the cut. To get the density matrix for the observer on the right, you want to take a trace on the left, which you accomplish by saying that on the left part, we actually require the initial and final states to be the same, and then we sum over them. That means we just erase half of the cut. The picture is the same, but on this semi-infinite cigar, we just have a cut only going from tau equals 0 to the horizon. The horizon here in Euclidean space means the tip of the cigar. So a path integral on the cigar with a semi-infinite cut, a cut that starts at the horizon and goes to infinity, gives the density matrix seen by the right observer. Now, what is this density matrix if you're making observations very far from the black hole? Very far from the black hole. So remember, we had this metric. Well, I'll do it in Euclidean signature, so it'd be tau squared, plus more stuff. Very far from the black hole, 2gm over r is just 0. And the metric just goes to, for r goes to infinity, the metric just goes to be tau squared plus dr squared plus r squared d omega squared. In other words, it's just the Euclidean metric, except that tau has a periodicity given by the inverse Hawking temperature. So for observations near infinity, the density matrix of the Hartle-Hawking Israel state is just an ordinary Minkowski space thermal density matrix at the Hawking temperature. The difference of the black hole from Minkowski space, from rindler space, is just that in the black hole, the effective Hawking temperature is constant at infinity, whereas in rindler space it goes to 0. That makes the effect much more clear-cut for the black hole, because you simply have thermal behavior with the standard Minkowski space Hamiltonian if you're far from the black hole. In equilibrium, here we're describing an equilibrium state. So the density matrix of the Hartle-Hawking Israel state for the right observer at infinity is thermal at the Hawking temperature. Thermal means that there's both incoming and outgoing radiation in thermal equilibrium. So what we learn from this discussion is that the black hole can be in equilibrium at the Hawking temperature, because the Hartle-Hawking Israel state is a concrete state of the quantum field that describes equilibrium between a black hole and radiation at the Hawking temperature. Yesterday, we did not describe a black hole in thermal equilibrium. Yesterday, we had a black hole radiating into empty space. Yesterday, the black hole formed in a low entropy state, and we asked what you would observe if you watched it a long time afterwards, and we found that thermal radiation would come out. So we learned yesterday that spontaneously a black hole will radiate at the Hawking temperature. By constructing the Hartle-Hawking Israel state, we've gotten a description of a black hole in equilibrium with radiation at the Hartle-Hawking Israel temperature. So the fact that this is possible is another side of the coin of what we computed yesterday. Now, I think I presented this as if the Hartle-Hawking Israel state is a state of ordinary matter, ordinary quantum fields, in the presence of quantum gravity. And in that context, we specify the path, the space-time on which we do the path integral. Let's draw back the picture again. Let's go back to the state before we took the density matrix. To construct psi HHI, well, we specified the initial value hypersurface in which we want to define the state, and then we specified the space-time in which we were going to do the path integral to construct the state. We took the space-time to be the black hole solution, but if your quantum field, for example, is a Maxwell field, you could take any other space-time and we would have gotten some other state. By taking the black hole, we got an interesting state that represented thermal equilibrium. So the ability to have thermal equilibrium at one particular temperature was a hallmark of the thermal nature of the black hole. But just to get some quantum state, we could have taken any space-time. One of the quantum fields, though, is the gravitational field itself. And in the case of the gravitational field itself, we can't specify what we want the space-time to be. All we can do with gravity is to fix boundary conditions and then let the theory decide what space-time it wants. Now, psi HI, the Hartle-Hawking Israel state also makes sense for gravity. Well, experts will know that there's an issue about an infrared divergence, which we could cut off by going to a negative cosmological constant. I don't want to discuss that issue today, though. So I'm going to be more informal. So the type of discussion we've given of the Hartle-Hawking Israel state still makes sense for gravity, but for gravity we need to reformulate it differently. For gravity, you can't specify the whole space-time in which you're going to do the path integral, because what the space-time is what the theory decides. In gravity, you can only fix boundary conditions on the quantum fields, and then the quantum fields themselves decide what the space-time is. So to construct this Hartle-Hawking state for gravity, what I would do is the following. I'd specify S. We're always allowed to do that. In other words, specifying S means I specify the topology of S, and I also specify the metric restricted to S. And that's allowed because the quantum wave function for gravity is a function of a metric on an initial value surface. So we're allowed to specify the metric and then compute the quantum wave function as a function of the metric. But we're also allowed to In gravity, we're also allowed to define asymptotic boundary conditions. And then gravity will decide on what the interior of the space-time should be. So if I'm interested in the Hartle-Hawking state, Israel state for gravity, since I know it's a thermal state, well, in ordinary quantum mechanics, how would I define a thermal state? Well, a thermal density matrix at inverse temperature beta, I would define by a path integral with imaginary time beta. And then at the two ends, I'd have quantum fields phi and phi prime. And then my thermal density matrix maybe I'll call it phi in and phi out. I would simply do a path integral normalized with phi in and phi out as initial and final conditions on an interval of length beta. That'll give a thermal density matrix. But a thermal density matrix can be considered to come from a two-sided state. There's the so-called thermophile double state. The thermophile double is a state in the tensor product of two Hilbert spaces. And it's given by a path integral over an interval of length beta over 2. And then we specify the states of two different quantum fields, psi, phi, and phi tilde. Do the same thing as before. Maybe I'll call them phi left and phi right. The boundary conditions are that at one end we have phi right, at the other end we have phi left. This we can interpret as a pure state of a two-sided Hilbert space. In Hilbert space language, it's up to a normalizing factor. Both systems are in states of energy E. Sorry. I'm afraid I'm rushing through this bit too fast. I'm going to slow down and explain it more systematically. A thermal density matrix I'm going to make a fresh start on what I said too quickly in the last 5 minutes. A thermal density matrix at T equals 1 over beta is rho equals 1 over the partition function times the sum over states of a projection operator on the state EI weighted by e to the minus beta EI. The states EI are eigenstates of the Hamiltonian of energy EI. So this is a mixed state thermal density matrix for a single Hilbert space. Now, an important fact about quantum mechanics is that every density matrix can be purified. That means every density matrix comes from a pure state on a double Hilbert space by integrating out the second side. In this case, I could take this Hilbert space, a wave function in a two-sided system, HL tensor H right. And I put both sides in the same energy EI. Both the left and the right states have energy EI. And now I have 1/2 of the thermal factor. And you'll see that the trace over H right of the pure state density matrix of the two-sided system well, let's take the trace over H left, which is the way we usually do it, is the density matrix for H right, the thermal density matrix of a one-sided system. So this is a general operation in quantum mechanics that broadly there are two ways to think about a thermal system. A thermal system has a mixed state density matrix as presented this way, but it's often convenient to think of that mixed state density matrix as coming from a pure state density matrix of a doubled system by tracing over the observations in one copy. So what I explained for the black hole was the 2 points of view. Right. I first introduced the state psi HHI. That was the pure state of a doubled system. HL tensor HR. Then we took the trace over the left to get the density matrix on the right, and that was the mixed state, which was thermal. So if we want to imitate this, when I presented the Hartle-Hawking Israel state, I did so for a quantum field in a fixed gravitational background that was up to us to specify. And we specified it to be the Euclidean version of the black hole. If we want to do the Hartle-Hawking Israel state for gravity itself, all we're allowed to specify is the geometry on the hypersurface S, the initial value surface, and the asymptotic boundary conditions. And for the asymptotic boundary conditions, we can specify the temperature which we want, which we would do by taking a Euclidean time of beta or beta over 2, depending on whether we want to construct the doubled pure state or the undoubled mixed state. So if I want to construct the pure state, the Hartle-Hawking Israel state for gravity, I would specify that this length, first of all, for that purpose, we only consider half of the spacetime. Let me erase the half we don't want. So I'd specify this boundary, the future boundary where the wave metric is specified, and also at infinity I'd specify that I want an imaginary time beta over 2. So in gravity, I'm allowed to specify that much. I'm allowed to specify asymptotic boundary conditions at infinity, and I'm also allowed to specify a metric on a codimension 1 initial value surface. The theory then decides what geometry it wants. And in the approximation of Newton's constant being very small, what the theory will do is to find a classical solution that satisfies the boundary conditions. And if you pick the metric on S to be the actual metric at time 0 of the Schwarzschild solution, then the classical solution the theory will pick will be the same one we've been talking about. So in gravity, the Hartle-Hawking Israel state is a state of the metric on S. And the metric on S could be anything. But if you pick a completely random metric on S, then the Hartle-Hawking state will be very small for that metric. If you want to ask, what are the, well, if you pick any metric at all, the theory will try to find a classical solution with that metric, but its action might be very big. If you want to ask, what are the metric that's likely? If you observe the metric on S in the Hartle-Hawking Israel state, what are you likely to see? You're likely to see something where there's a simple classical solution whose action isn't too big. And that's the actual metric of the Schwarzschild solution. That is a maximum of the Hartle-Hawking Israel wave function. And for that one, the metric the theory will pick will be simply the black hole solution. If you're close to this, the theory will pick something that's close to the black hole solution. So in the approximation of treating gravity semi-classically, what it means to describe the Hartle-Hawking Israel state of gravity is that you pick a metric that's close to the actual Schwarzschild metric, you specify at infinity that you want imaginary time beta over 2, and then the theory will pick approximately the black hole solution with small fluctuations around it, because you'll have to do, in quantum mechanically, you allow for fluctuations around the classical solution. And if this isn't exactly the Schwarzschild metric, then the classical solution will be a little bit different. But anyway, in the classical limit, there's a Hartle-Hawking Israel state for gravity that's quite similar to the Hartle-Hawking Israel state for other quantum fields, except it takes longer to explain. And I even got into a tangle in trying to explain it, where I tried to shorten the discussion too much. Any questions on this? Okay. This particular time, though, I'm concerned that the lack of questions is because I've confused you rather than because it was clear.
Questions, comments? But we can continue.
Okay.
On which grounds do you have control over the maximum of the wave functions?
That's a general question. The question is, how do we ever understand a quantum mechanical wave function? For weak coupling, we try to find a classical solution that dominates, and we hope for the best.
Thank you.
Okay, now we're going to use this point of view to calculate the entropy of a black hole, with the goal of recovering yesterday's answer from a Euclidean point of view. So the entropy is minus the trace of rho log rho, which is minus d by dn of the trace of rho to the n evaluated at n equals 1. So in the Rindler case, rho was e to the minus 2 pi k r divided by a normalizing factor. And in the black hole case, rho is e to the minus the Hawking, well, beta Hawking. I'll just call it beta. Well, okay. Yesterday, we started with an assumed mass of the black hole, and we computed beta. Today, it makes more sense to specify beta and then compute m. Because at infinity, what we're allowed to do is to specify beta. And then having specified beta, the theory is going to pick what geometry it wants. So the theory will decide on m. So we should invert the formula. So today we just specify beta by saying that we're going to put a beta over 2 here. Well, a beta over 2 in computing the state, but a beta in computing the density matrix. Right? The density matrix. To get the density matrix, we specify the geometry on a partial space-time that ends somewhere. And we specify at infinity we want imaginary time beta. And then the theory looks for the solution. And it will pick a mass that depends on what we assume for beta. So yesterday we computed that beta was 8 pi gm. But in today's approach, we specify beta, and we might learn that m is beta over 8 pi g. But we haven't learned it yet. We're going to learn it. So our rho is e to the minus beta h divided by a normalizing factor, which is the thermal partition function. And then what's rho to the n? Well, it's 1 over z to the n times e to the minus beta n times h. So e to the minus beta nh is almost the partition function at a different temperature, beta n, except that the partition function at temperature beta, inverse temperature beta n, would have needed a different normalizing factor. Here we get a normalizing factor that's just the nth power of z beta. Z beta to the n is not equal to z n beta. That's why we're going to get something non-trivial. If we put here z of n beta, then the trace of rho to the n would have been 1. Because if I put here z of n beta, then the right-hand side of the normalized density matrix's trace is 1. It will actually have the wrong normalization factor, which is going to lead to our answer in a little while. Okay. So we need to compute the trace of rho to the n beta h of the black hole. So well, how do we compute the trace of e to the... Oh, okay. First, how would we compute the trace of e to the minus beta h? It's actually easier than all this discussion of the Hartle-Hawking Israel state, because we just have periodic imaginary time at infinity, and then the theory does what it wants inside. And for weak coupling, it will create a classical solution inside. And that classical solution will have to be, well, we'll assume the classical solution is a black hole with the appropriate thermal period of beta. So it'll be a black hole with a mass which is m of beta. And then we'll approximate this trace by the exponential of minus the action of a black hole with m equals m of beta. So we're going to just approximate our path integrals by exponentials of classical actions. That's supposed to give us a leading approximation for weak coupling. So remember, the Hartle-Hawking Bekenstein entropy is A over 4G. So it's very big when G is small. It's A over 4G plus S out. S out is of order 1, but A over 4G is of order 1 over G. The 1 over G term is going to come from a classical action. So what we're going to do is to try to get this term just from the classical action of the black hole solution. So exponential minus the action of a black hole at inverse temperature equals beta n is going to be our approximation to the trace of e to the minus beta n times h. Now, there are two reasons you can give, both of which are wrong, but there are two obvious reasons to try to prove that this is going to give a trivial answer. So we have to ask, what is the action of the black hole solution at some inverse? Well, we'll want the inverse temperature beta n, but we could ask, what is the action of a black hole temperature at any inverse temperature beta? In our application, beta will be beta n, but for any beta, what's the action of this spacetime? Well, I'll give two reasons to try to prove it's independent of beta. Of course, if it's independent of beta, it will be independent of n, and our derivative with respect to n won't be very interesting. So both of these reasons have to be wrong. But I'll give two ways to try to prove the answer is trivial. First way you could try to prove it's trivial is that the Einstein-Hilbert action, I think I've been calling it I, the Einstein-Hilbert action is minus 1 over 16 pi g times the integral of the Ricci scalar. But r equals 0 for a classical solution. So the action is 0. So this is the first claim you might make. Well, there's something wrong with that claim, though. If you're studying a boundary value problem in quantum field theory where you specify the fields on the boundary, that only works if the action is only first order and derivatives. But the Ricci scalar has the second derivative of the metric in it. And to compensate for that, you need to add to the action a boundary term, which is the Hartle-Hawking, the Gibbons-Hawking-York term. So the action really requires a boundary correction due to Gibbons, Hawking, and York. Which involves what's called the extrinsic curvature. It's needed because the Ricci scalar involves the second derivatives of the metric. In general, well, if you had a free particle, the usual action is 1/2 x dot squared. And that's good. But you could have gotten the same classical equation of motion if you took the action as -1/2 xx double dot. You'd find, though, that if you study a boundary value problem, this one behaves well, and this one doesn't behave well. And you don't usually worry about that because you're usually never tempted to use this one. Now, first of all, the reason this gives the right equation of motion is that they differ by a total derivative. They differ by a total derivative that can be expressed as a boundary term. So if you really wanted to use this action, that would be fine in the bulk. But if you ever want to study a boundary value problem to construct a quantum state by path integral, you would need to add a boundary term, which would amount to going back to this action. And textbooks don't usually explain this because you're not usually interested in this action. Why would you do that? This is the natural way that you've heard about the Lagrangian since the first time you studied it in classical mechanics. Gravity is the only bad case, from this point of view, where there's no natural way to write the bulk action without second derivatives. So gravity is the case where this is the only version of the action that's available, and therefore it's important to add a boundary term, when you study a boundary value problem. And the right boundary term was computed by Gibbons-Hawking and Yerk. So with the help of that boundary term, the action is not 0 and does depend non-trivially on beta. And if you calculate the action using the boundary term, and use this to get the trace of rho to the n, and then you calculate the entropy as minus d by dn of the trace of rho to the n over the normalizing factor at n equals 1. The normalizing factor is part of the definition of rho. If you compute the action and then put it in this formula, you will, after a little while, get the same formula we had for the entropy yesterday. The only trouble with that derivation is that it doesn't explain why the answer is proportional to the horizon area. Because in this approach, you'd calculate the answer by measuring a boundary term at infinity. And it will be true for the actual Schwarzschild geometry that that boundary term you measure at infinity is equal to a over 4g. But that will look a little bit like a miracle. And I want to, instead of doing the computation that way, explain the calculation in a way that makes obvious that the answer is going to be a over 4g. Rather than, we could carry out this calculation to the ends, we'll get an answer, and then we'll compare it to a over 4g, and we'll see, lo and behold, they're equal. But we won't quite, if we do it that way, we won't quite feel we know why we got a over 4g. I want to do the calculation in a way which will make it obvious that the answer is a constant times the area of the horizon. So I'll head in that direction in a moment, but I do want to give a chance for any questions on what I said here.
I get that the first argument has to be wrong, but just to be the devil's advocate, can it help to consider Palatini formalism so that we only have first derivatives in the connection variable?
I'm sure it helps, but I haven't planned to explain what we get if we do it that way. Well, this is the correct version of the action, so it will also be correct in the other formalism. But I can't instantly tell you what to say. I think maybe what happens in that formalism, see, a step here was that I said that the action was 0 because of the equations of motion. I think maybe that step will be wrong in the Palatini formalism, and you'll instead only prove from the equations of motion that the action is a total derivative. I'm not sure, though. I'm winging it because I didn't plan on that question. Sure. Anything else? Yes? Just speak up.
So I understand why you are computing the saddle point approximation on the black hole solution.
Yes.
In principle, you could consider also at temperature T, some gas of graviton at an equilibrium, but you are not computing that contribution. Can you comment about it?
Well, Gibbons and Hawking originally presented it the way I have, which is that we just decide to study the black hole, and we don't worry about why we could have done the other. A later answer is, which actually was largely due to Hawking and Page, is that with a negative cosmological constant, the black hole at high enough temperature actually dominates the thermal ensemble. But in the Minkowski space version, you have to just decide you want to study the black hole.
So this domination, you cannot decide?
Well, in flat space, the thermal ensemble, in asymptotically flat space, the gravitational ensemble is really unstable because a constant energy density produces a black hole. So if you ask questions about this calculation, which are too deep, then we will have to answer them by going to anti-de Sitter space, which, however, I didn't really want to do because I haven't presented ADS-CFT duality in the lectures, although it would be familiar to many of you. But that's the kind of answer we'll have to give if detailed questions are asked. Any other questions? Okay. We're studying the black hole because we want to, but in higher orders, we won't just have a classical solution. We'll have quantum fluctuations in the black hole spacetime. So in today's approximation, the path integral is the exponential of minus the classical action. But in the next approximation, it would be that times a one-loop determinant, then with higher corrections. And the one-loop determinant will give us the contribution of the gauges of gravitons in the field of the black hole. Okay. Now we're going to discuss a second attempt to prove that this is independent of beta and therefore uninteresting. And again, it will be wrong, but it will tell us what to do instead. Now we argue that whenever you have a classical solution, so here's the second wrong argument. We're going to say that the classical equations of motion say that the action is stationary under any variation of the fields. And therefore, we'd say that changing beta is an example of a variation of the fields. So therefore, well, this is the wrong step, but therefore we'd say that the action is independent of beta. Well, what's wrong with that argument? Well, what's wrong with that argument is that when you prove the equations of motion by saying that the action should be stationary, you have to integrate by parts, and there's a surface term involved. And the correct statement is that the variation of the action is 0 under field variations that are trivial at infinity. In other words, the correct statement is not that the action is stationary under field variations. It's stationary under compactly supported field variations, or under field variations that vanish fast enough at infinity, but not literally under all field variations. And here we're changing beta, which is the asymptotic behavior at infinity. And so the action can depend on beta, and it does, as we would have found in the first calculation if we had evaluated the Gibbons-Hawking-York term. That term will depend on beta, although this doesn't. Now, however, we're going to use the fact that we only want to vary beta slightly. We only want to work to first order in beta. Because all we want to do is to vary, we want to differentiate with respect to n at n equals 1, the trace of rho to the beta n. So that's like differentiating with respect to beta. So we only want to know what happens if we change beta to first order. So if we're only going to change beta to first order, it doesn't matter whether we obey the classical equations or not in the variation, because the action is stationary under all variations that vanish at infinity. So if you take any two variations that change beta by the same amount at infinity, they differ by a variation that vanishes at infinity, and therefore they will give the same action. This is an extremely simple, but also subtle and key point. When we vary beta to first order, we can do one of two things. We want to calculate the action under a first order change in beta. And one is we could satisfy the equations of motion. That means that when we change beta, we replace the Schwarzschild solution by an appropriate solution with the new beta. If we do that, we could, of course, work to all orders in beta. There's no reason to only make a small change in beta. But to first order in beta, we could do something which is more convenient. Any variation at all that changes beta in the right amount is going to give the same change in the action to first order in beta. That's true because we're starting at a classical solution. And at a classical solution, the action is invariant under variations that are trivial at infinity. That means that any two variations that are the same at infinity produce the same change in the action because their difference is trivial at infinity. So we're going to look for a more convenient change in the metric that has the same change at infinity. And here's how we do it. We take this metric, and we make literally no beta-dependent change in the metric. We just say that tau is going to be equivalent to tau plus beta, whatever beta is. At the beta we started with, and we keep m fixed. At the beta we started with, it was correctly related to m so that the metric was smooth. Now when we change beta, well, let me be explicit about it. We'll replace beta by beta n. Now when n is not 1, but we use the old metric, it's no longer smooth at the horizon. Now it's got a conical singularity. If n is slightly less than 1, the geometry would look like this. Well, I've drawn it as if n is a lot less than 1. This angle is now 2 pi n. So when n is 1, the angle was 2 pi and it was smooth. If n isn't 1, we have the wrong periodicity and the metric is singular. This is not a classical solution of Einstein's equations because the scalar curvature has a delta function at the apex of the cone. But to first order in beta, this is a way of changing the period from beta to beta n. And therefore, to first order in beta, it will give the correct formula for the action. Now, it's very easy to calculate. Rho, remember, was a normalizing factor times e to the minus beta h. And then rho to the n is this. Now, we now have a metric that has a conical singularity at the origin because beta was replaced by beta n. Away from the origin, the period is multiplied by n, so the action is multiplied by n. So, okay. This is going to be 1 over z to the n times e to the minus beta n, e to the minus n times the action before. The I beta is the old action. But there's also going to be a new term in the action. The new term in the action will be there, and we'll evaluate it in a second, because the metric is now not a classical solution at the horizon, and that will give an additional contribution to the action. But the old action, whatever it is, isn't going to do anything, because at n equals 1, it canceled the normalizing factor, and after multiplying, taking them both to the nth power, they still cancel. So we don't really need to evaluate the old part of the action because it just cancels the normalizing factor. So in this approach, it's manifest that the answer will only come from the new part of the action. The new part of the action arises because the classical equations are not satisfied at the horizon anymore, and the scalar curvature actually has a delta function. What you need to know is that if you have a cone with an angle theta, the scalar curvature is a delta function supported at the apex times 2 pi minus theta times some constant that I checked yesterday. Sorry. Gosh. Well, whatever I need to know this constant, I figure it out as follows. Take a square, and then take two squares and glue them together. So glue opposite corresponding sides on each of two squares. What you've made topologically is a sphere. But it has four singularities at each of which theta is pi. Now, on a sphere, the integral of the scalar curvature is 8 pi. And that's equal to 2 pi minus theta, which is pi. Well, there are four of them, times 2, I think. So I think by that computation we learned that r is 2 times 2 pi minus theta. Hope I did that correctly. I checked it yesterday. Okay. Yeah, okay. I think that agrees with what is in my notes, so I think it's correct. Okay. Our homework is to check that calculation. But anyway, it is true that the scalar curvature is a delta function times 2 pi minus theta times something, but in our application, theta is 2 pi n. So in our application, this is 4 pi times 1 minus n times a delta function. And therefore, the part of the action we're interested in, I nu, only comes from here. And it's minus 1 over 16 pi g times 4 pi times 1 minus n, or minus 4 pi times n minus 1. And then we have to integrate a delta function. But you have to remember that we usually don't talk about the sphere, the extra polar angles. And that gives a factor of the area. So the new action is a over 4g times n minus 1. And therefore, the entropy is minus the trace of rho log rho, which is minus d by dn at n equals 1 of the trace of rho to the n. It's minus d by dn at n equals 1 of the exponential of minus this new action, or minus d by dn at n equals 1 of the exponential of minus a over 4g times n minus 1, or a over 4g. So that's a version of the derivation where it's obvious that the answer is proportional to the area, because the area was just a trivial factor. We had to evaluate the action at the horizon, but there was this factor of n minus 1 over 4g that came by integrating over the radius and the time, but the angles just trivially gave a factor of the area. So in this derivation, it was obvious that the answer for the entropy is a universal multiple of the horizon area. The derivation that I didn't explain to the end, where we would have computed the Gibbons-Hawkins-York surface term in the action, of course gives the same answer. Now I think this is a reasonable point to stop, but at this point I'm going to revise the plan for tomorrow's lecture. Tomorrow's lecture will be the things I didn't get to today, which are going to be Cassini's explanation of the Bekenstein bound and Aaron Wolff's proof of the generalized second law.
So we have time for more questions. There are? And comments?
Okay, so to get to this final point of this proof, in the end, what we basically made our our transformation was rescaling the beta in the apex to get this. It's not clear to me exactly what was the transformation, the first order variation that we made in all this setup. And
Oh, well, remember, we wanted to compute the variation of the action with respect to beta.
yes.
And to do that, we could literally take any variation of the metric where we change beta at infinity. What we do inside doesn't matter because we started at a classical solution, so variations inside don't matter. Now, the metric we started with was this one that I keep writing and unfortunately erasing, where tau is equivalent to tau plus beta. I want tau to have a different period, and I'm allowed to use any change in the metric where the period of tau changes. Yeah, okay. So just I brutally say the metric is the same, but tau has a different period.
Okay.
So the metric is given by the same formula, but tau has a different period. That's an example of a new metric with a different period at infinity. It doesn't satisfy Einstein's equations everywhere. It fails to satisfy Einstein's equation at the horizon. But it has the property that away from the horizon, the action is trivially proportional to n. Because when you integrate over time, instead of getting a factor of beta, you now get a factor of beta n. And because the action is proportional to beta n, to n, when we do this, you see, if the action is proportional to n, then trace rho to the n would be e to the minus n times something. And since z was chosen so that these cancel when n is 1, they trivially cancel for any n. So there were really two advantages of doing it the way I did. One is that we didn't have to calculate the bulk action because it trivially cancels. So that saved us the work of analyzing the Gibbons-Hawking York term. But the second is more important, perhaps, and more conceptual. The second is that we had a way to do the calculation that made it manifest that the answer is a multiple of the horizon area.
So it appears to me, have we ever assumed n to be small in this transformation?
Yes, we did, because the entropy, the reason we use, not small, but near 1, the entropy is the derivative with respect to n at n equals 1 of trace of rho to the n. Sorry, I've put the z in the wrong place. It's not here. It's when we write rho to the n in terms of the action.
Yes, but I understand.
Since we're only differentiating with respect to n at n equals 1, that means that n minus 1 is infinitesimal.
Yes, true. But what I wanted to say is, I mean, if we had assumed this n to be, for example, n minus 1 to be 3,
yes. Then we could not do this
derivation
calculation.
would have been wrong.
What would have been wrong?
In this derivation.
Well, it's only true to first order that it doesn't matter how we vary the metric. When you have a classical solution, any two variations that are the same at infinity give the same change in the action in first order, but only in first order. So we used something that was only true to first order in n minus 1. Okay. But that was sufficient to calculate the derivative with respect to n at n equals 1.
Okay, yeah, thanks.
Any more questions?
So I can't understand what's the main difference between Hawking temperature and Rindler, the Hurre temperature. So I can't understand why the periodicity term goes to 0 in the Rindler cases and why not in the Schwarzschild solution. What's the main difference between these two
Well,
cases?
the main difference is that in the black hole case, the period remains finite at infinity. In the Rindler case, the picture corresponding to this one was just the plane. And at radius r, the period is 2 pi r. So in the plane, a circle of radius r has a diameter of 2 pi r. In the black hole, radius r means you go out to radius r, and then you take a circle, and the diameter of that circle is independent of r for large r.
Yeah, but in the large R limit, the Sparsi solution becomes flat. So in the large R limit, why they do the same things?
Well, the fact that it's flat is good news. So in the large R limit, it's R3 times a circle of period beta. And before my lectures, hopefully some of you were exposed to the fact that a thermal ensemble in quantum field theory in Minkowski space can be described by a path integral on R3 times a circle of radius beta, circumference beta. If you're familiar with that, then you'll see that what we got far away from the black hole goes over to a standard description of the thermal ensemble at inverse temperature beta. If you're not familiar with it, you should brush up on the standard thermodynamics of the quantum field, and then you'll understand better what I'm saying.
Okay, thank you, I understand.
So in the derivation that you've presented, we built with the Euclidean path integral a state on the initial value surface.
Yes.
If, for example, we are interested in black hole evaporation,
Yes.
I imagine that we have to consider another surface. Is it possible to use similar arguments, or maybe we have to consider a Lorentzian path integral to define a state on a different surface? How the argument changes in this setting?
Well, the usual technique is to use a Euclidean path integral to define a state, but then study the state in Lorentz signature.
Sorry, I didn't understand the last part.
Well, if you've never seen it done, you will have trouble understanding it from my description. It would take another lecture to really explain it well. But the usual approach to such things is to define the state by a Euclidean path integral, and then to study it by looking at Lorentz signature correlation functions in that state.
Okay, so
it's going to be difficult to give a better answer than that right now.
So we define a state on a different surface, still using the Euclidean path integral?
No. The Euclidean path integral defines the state the way we did. Then it's up to you what questions you want to ask about the state. You can ask, okay. In ordinary statistical mechanics, you can study real-time correlation functions. How do you do that? Well, first let's discuss what you want to. What is a real-time correlation function? First of all, you have a thermal density matrix. If you want to describe that density matrix by a path integral, it will be a Euclidean path integral. That's just a fact of life, because you're interested in e to the minus beta h instead of e to the minus ih beta or t. But you could study a real-time correlation function in a thermal ensemble. For example, take a thermal ensemble, disturb it at time 0, and ask what you'll see at time t, where t is real. That question makes sense. The way you answer that question is by computing a real-time correlator So in the thermal ensemble, you want to ask, on the average, if you perturb it at time 0 and measure at real-time t, what will you see? Well, mathematically, you're trying to compute this. So if you want to think in terms of a state and a correlation function, it's a bit of a hybrid, because the state would be defined most naturally by a Euclidean path integral, but you're asking a Lorentz signature question about it. So in general, you're asking me, how do you study real-time behavior of a thermal ensemble? And I was trying to give you a schematic answer to that question.
Okay, thanks. Maybe I wasn't clear. I was thinking of studying the density, the von Neumann entropy of a state that's defined on another surface?
Oh, well, it will be the same because under unitary evolution, the von Neumann entropy doesn't change.
Okay, and if we want to reduce the density matrix on a slice, on a subset of the slice, for example, to compute the entropy of radiation in what we considered yesterday?
The Hartle-Hawking Israel state is not a good starting point for that because it is a state of the black hole in equilibrium. So for the question you've just asked, you need to study a different state of the black hole, which you should have prepared differently. But you probably prepared it by a Euclidean path integral, a different one. And then you're asking about a real-time question about a state that you prepared probably by Euclidean path integral.
Okay, thanks.
Any more questions, comments, observations?
Okay, this has got to do with a previous part where you talked about the Hartle-Hawking Israel state. So you said that if we go to gravity and we make it dynamical, so we are not allowed to fix a background geometry. What we are allowed to fix is a surface, an initial value surface with its time periodicity and the metric on it, and we can study how it behaves for different metrics to find which is the semi-classical one by having the highest probability. Is this correct?
We don't specify the periodicity. We specify the asymptotic behavior at infinity and the initial value surface.
Okay, so we only specify it at infinity, how it behaves, like this.
Well, everywhere at time 0,
yes,
and at all times at infinity.
Okay, okay. Thanks for the clear.
More questions? We had enough questions, so we can really talk. We can thank again Professor Witten. And we can meet back again tomorrow at 10:30 for the third and last lecture.